Welcome to Spreadsheet Geek. In this video, we'll take a look at optimizing our manufacturing costs. We have orders for 5 different types of widgets. All of these widgets have different cycle times. We can choose from 5 different machines to make the widgets on, and we have 5 different employees paid 5 different labor rates who can operate the machines. We'll lay all of this information out in a spreadsheet and use Excel's solver add-in to find a solution to our problem. By the end of the video, you'll have an understanding of how to use Excel's solver add-in and how it can help you find solutions to complex problems. This video was made using Microsoft Excel 2019. Before we get started, we need to make sure Excel's solver add-in is turned on. To do that, go to your File menu, Options, click on Add-ins, go to the bottom where it says Manage Excel Add-ins and hit Go, and put a check in the box of the solver add-in. After you do that, when you go to the Data tab, you'll see Solver over here in the Analyze column. You might want to turn it off when you're not using it because it can, depending on your system, increase the processing time of Excel. Let's jump right into our problem. We make widgets. It's not really important what they are, but these widgets require a manufacturing process to complete. We have 5 different orders from 5 different customers for 5 different widgets. And they've ordered these quantities, and we've pre-agreed to these sales prices. We have a valid purchase order from these customers. When we complete the sale of these widgets to these customers, it will result in these levels of income to total about $148,000. We also have a number of other givens. There is a certain amount of raw materials, I'll abbreviate it RM in this presentation. Those raw materials go into each type of widget. For example, widget A needs $2 worth of raw materials going into each unit. So if you multiply the quantity ordered by the raw materials cost, you get to this number. So this is our total for raw materials for these jobs. These raw materials costs were prearranged. We have a contract with our supplier, so those are non-negotiable, and this is a fixed amount that we have to deal with. Another characteristic of our widgets we need to take into account is the cycle time needed to produce them. Cycle time is 35 seconds for widget A and 40 seconds for widget B, and so on. This is linked to the product, not to the machine. So regardless of which machine we produce widget B on, it's going to take 40 seconds. I'm going to add on 2 more columns of information. One is production units per hour. So I'm just going to take the number of seconds in an hour, which is 3,600, and divide by my cycle time. And that'll give me the number of units I can produce of this type of widget each hour. Another thing I'd like to calculate is my total run time for each job. So that'll just equal the number of units I need, which is over here, and I'll divide by the number of units I can produce in an hour. So this job should take about 58.3 hours, and we'll fill that in. Now the resources that we have to complete these 5 jobs are these 5 machines. So these are machines 1 through 5. They go from oldest, which is a 1992 model, to the youngest, a 2019 model. They have different setup costs. Now the setup cost is a one-time thing, a one-time fixed cost per widget job. So to set up any widget on machine number 1 is going to cost $300. This task is performed by a technician on the graveyard shift, and he gets it ready to go for production. There is nothing we can do about this, but Once the machine is set up to produce widgets, the production worker can come in and he can just flip the machine on and then flip it off at the end of the day. And if the production run goes multiple days, there's no additional setups required. It's one setup per job. In addition to setup cost, we have a cost per hour, which is primarily tied to energy usage. So this old 1992 machine has a cost per hour to operate of $90, and the newest machine is much more efficient at $50. The other resource we have to finish these jobs is our pool of production workers. We have 5. They earn these labor rates. And any of these 5 people can operate any of these 5 machines. They're all interchangeable. We do have a policy that once we assign one of these production operators to a particular job, we let that employee finish the job, and we don't generally swap out production workers once they start working on a job. Understand that we don't necessarily have to worry about keeping all of these workers gainfully employed after these 5 jobs are complete. There will be other jobs for them to do at that point that are not listed here. They'll all finish up within a day or two of each other given these run times. So to sum up our problem, we have 5 jobs, 5 machines, and 5 employees, and we need to assign those employees and machines in such a way as to reduce our manufacturing cost to the lowest level possible. Now, somebody might suggest that we simply use the cheapest employee and the cheapest machine and do all 5 jobs on that. Well, that's not an option. We need to keep these 5 employees employed, and if we tell 4 of them to go home, then they're probably going to quit and go work somewhere else. So we've been given these 5 employees for a reason. We need to complete these jobs in a timely manner for our customers. So let's get started on assigning these resources to these jobs. So everything listed here so far is basically a given for the problem. And what I need to do now is lay out a number of cells, and one of those cells will be my designated objective cell. That's what Solver needs. And the objective cell is usually either a cell you want to maximize or minimize. So in this case, I'm going to make that manufacturing cost, total manufacturing cost, including labor, machine cost, setup cost, and material cost. I'm going to put it all into one table, and I'll put constraints on some of those cells, and we'll find a clever way to process this through Solver and come up with the best possible solution. The first thing I've done here is just list my different jobs, and I pulled down my raw materials total cost from this column. So our total manufacturing cost is going to be that raw materials cost plus our labor cost plus our machine cost. So I'm going to tackle these in the order of how easy they are. Raw materials was very easy. It's just a direct copy from what we already calculated. The next one will be the employee and labor cost. And just to kind of tie these together, I'm going to highlight these in blue. I really just need this column in which to calculate my labor cost for each widget job. I don't really need this, but this is going to be used by Solver. It's going to try different values in this column for employee number, and that'll result in different labor costs. So think of it this way. Solver's going to put a 1 through 5 in each of these cells, and those will be mutually exclusive. So it'll try a 1 here, and then it's got to use 2 through 5 in this cell, and then whatever's left over in this cell. And then over here, based on what I see here, I'm going to have a complex if-then statement with nested ifs to determine the labor cost. So let's just set one up. I'm going to put this at 1. We'll say employee 1 is going to do this widget A job. So what's my labor cost? Well, if this cell equals 1, then my labor cost is going to be this. This is widget A times employee number 1's wage. And if that is not true, here's where I'm going to enter another if-then statement. If this cell equals 2, then we have this times employee number 2's rate. Another nested if. If this equals 3, my labor cost will be this times employee number 3's wage. And finally, if this cell equals 4, then my labor component will be this amount times employee number 4's. And for the last one, you don't nest another if, you can just enter the remaining possibility, which is this our hourly amount times employee 5's hourly rate. And close that off. So let's see if these are right. Employee 1 equals this times this. 1283. What if we change this to 4? Then I can change this to H13. Looks like that's working well. Now, to save me a lot of trouble of repeating that whole tedious exercise, I'm going to just autofill this down. But before I autofill it down, I need to decide on what's going to be a relative reference and what's going to be an absolute reference. So I know this K2 cell is only for this line, so I want that to float. I want the C17 to float. The ones I don't want to float are the H values. So let's hit F4 on all of those. Should be 5 of them. 4 and 5. Now let's fill that down. Let's enter some other numbers in here. What am I missing? 5. So let's calculate a couple of these to make sure this is working right. So if widget C is done by employee 2, that would be this number of hours times 1579. So that looks like that works. Let's check one more. Employee 5 is doing widget E. So that would equal this wage, or hours times this wage. 1233. So those look like they're working correctly. Let's move on to the machines. So I've added 2 very similar columns here to these 2 columns. And I've highlighted these in red just to kind of tie them together. So let's enter a machine here. Let's pick number 1 again. So if machine 1 is used for the widget A job, how much will my machine cost be? If this equals 1, then my machine cost is machine 1's setup cost plus widget A's time times the cost per hour. Nest another if. If this equals 2, the value, if true, for number 2 would be this plus my hours required times the hourly rate. If this equals 3, my machine cost will be the hourly rate, or the setup cost for number 3, plus the hours times the rate for that machine. And finally, if it's 4, I need that setup cost plus my runtime times the hourly rate for machine number 4. And the final alternative is this plus this times the hourly rate for machine number 5. And I think I've got an extra pair in there. I think it fixed it. So let's take a look at our formula and get it ready to paste down. What do we want to make an absolute reference? Well, it looks like these values here in column C and D, we always want those to stay the same. So I'm just going to hit F4 on all the C's and D's. C, D. And we'll autofill that down to save a lot of trouble. Let's fill in some numbers here. And I'm just going to spot check one of them. If machine number 2 is used for widget C, that would equal the setup cost plus, what did I say, number C times the hourly rate. 46.74, so that looks good. So I turned everything back to black and I added one more column for the total. So the total will just equal the parts or raw materials plus the labor plus the machine time and setup. So we'll paste those down and I need to total that up. This is going to be my objective cell right here. This is what I want to minimize. I'm also going to need sums in this cell as well as this cell. So let's put some lines in there. This is going to be key to controlling my results. I only have 5 machines and 5 employees, so I can't use the same one twice. So I'm going to set constraints on these cells that they have to be a value between 1 and 5, and they also have to be different from each other. Same constraints here, and the constraint on this cell is that it must add to 15 for both of them. That way we'll guarantee that Solver gives us only workable solutions. At this point, we're ready to open up Solver. There's one thing I'm going to do first, and that is I'm going to just highlight these constraint cells with a color and my objective cell with a different color. So let's open up Solver. You get a dialog box like this. It asks you what the objective is. The objective cell for us is going to be right here. And we want to set that to a minimum possible value by changing these cells, and I'll separate these with a comma, and these cells. Now we're going to put in a number of constraints on these orange cells. So let's start adding our constraints. For these cells, they need to be greater than or equal to 1. And the same thing for these cells. These cells need to be less than or equal to 5. And the same for these cells. These cells need to be integers, and there's an option for that, as well as these cells. Finally, these cells need to be all different. So there's an option for that as well. Same goes for these cells. Now there's a couple other cells that have constraints on them, and it's this cell, which needs to be equal to exactly 15. And the same for this cell. You can review all of your constraints here in one place. There's a checkbox here to make unconstrained variables non-negative, so unconstrained variables positive. That defaults to checked, and I think that's what we want. And then you can select a solving method. Now there's some other Excel tutorials out there that put out some guidance on this. First, if you have a linear function or a linear relationship between all your variables, in my mind that would be like a two variable, fairly simple scenario. You want to select simplex LP. Now if you have nonlinear, you can select GRG, nonlinear, or evolutionary. One of the recommendations out there is to select GRG nonlinear first, and that evolutionary takes longer. With this scenario that we're doing today, I have actually found the exact opposite to be true. The GRG nonlinear works, but it takes a very long time. It runs about 80,000 trials. The evolutionary is much quicker. It runs about half that, and they basically got to the same answer. The thing that went wrong with GRG linear is when I reversed this to max, it didn't work. But with the evolutionary, you can flip back and forth. So after we run the minimum value for our manufacturing cost, I want to see the maximum value so I can compare the two and see how much we potentially saved on our manufacturing costs. So we're going to use the evolutionary today, and I'm going to hit the solve button. And you can see down here in the left corner, there's trials being run, and I will check back when this is done. Okay, I'm back, and with the evolutionary method, that took about a minute, maybe just slightly longer. And it says, solver cannot improve the current solution. All constraints are satisfied. So I've got a solution here of 84,161. I'm going to say OK to that. I've made a note of that. And what I'm going to do now is go back into Solver. And I'm going to look and see if I can figure out what the maximum will be. What's the worst case scenario? And we'll run that one. So that result is back, and I'm coming up with 84,804. By the way, you can save these scenarios. And when you do that, they go right into Scenario Manager. So I'll say OK to that. And if you go up here to Scenario Manager, you will see that our max scenario now can be recalled. Now, if you run these over and over again, you may get a slightly different result, especially with that GRG method. With the GRG method, I ran the minimums 4 different times and I got 4 different answers, and it took a very long time each time. With the evolutionary method, I always came up with the same minimum, which is this value, and the same maximum. It seems to be more consistent. And interestingly, the evolutionary method minimum is lower than any of the minimums that I came up with from the GRG method. So I'm not saying the guidance out there is bad. It may be particular to my problem here that causes the evolutionary method to work better. That concludes my demo. If you know a better way to solve this manufacturing optimization problem, I'd like to hear about it in the comments. Please let me know if there's a better way. And I hope you've enjoyed this video. I'll be making more like it in the coming weeks. Please consider hitting my subscribe button, and thank you for visiting Spreadsheet Geek.